So how's everyone been doing with quarantine?
I've been okay.
Anyone else going slowly but surely insane?
Yeah, I can kind of feel it.
There. Is that, oh, I'm muted. Okay. Oh, wait, did you say you, wait. I'm not sure. Oh, no, that one's off. Okay, so I don't know what happened. I've been having technical problems all day. I'm on a laptop now. This is a much worse resolution, and I'm not really sure how I'm going to turn this into a document camera. But my mic just failed. So, and my mic and camera, it's just not making a connection for some reason. Well, hi, and I'm sorry about the delay. Can I begin by saying that I had a chance to meet with most of you guys yesterday, and it was actually very interesting. I enjoyed having a chance to talk with you one-on-one. We probably should have done that earlier in the semester just so I could get a sense of how you guys are doing. As I told each of you individually, the exams went pretty well. I haven't yet finished writing up an answer key, but I'm going to do that for you. I have gotten some additional homework problems for you, and I put them up online. I realized I did not set a due date, but maybe if you could turn them in a week from today, that would be good. It'll be all on chapter 9. So, does anybody have any further questions about either the exam or the, well, I guess, or the homework or the material that we were starting, that we've been going through in the last couple of days? Is everybody still there? Everybody got really quiet.
Yeah, sorry, I'm here.
Oh,
yeah, I have a quick question.
yes, certainly.
Hold on, give me just a moment.
Certainly.
So I noticed there was a part in our notes that said, like, when it comes to orders, if P divides X, then an order does not exist.
Correct.
Is that also the case for X divides P?
Well, I'm assuming that you're talking about a prime P. I mean, there's not too many divisors for a prime except for 1 and P itself. So if X and P are equal, then each one of them divides each other. And yes, in that case, the number X has no order. But the other possibility is, what if X is equal to 1? 1 divides P, but 1 does have an order. The order of 1 is 1. Right? So the order is the smallest positive exponent that you can put on the number to get something that's congruent to 1, and 1 to the first power is congruent to 1. So 1 does have an order. I'm not sure why you're asking about X dividing P. The big question is P dividing X.
Okay.
And I should say more generally that you're referring to when I was first talking about orders of elements. And I did that in the context of just working inside Z mod P, where P is a prime. And okay, in that case, exactly the elements that do not have an order are the numbers that are divisible by P. Now, when I say divisible by P, remember that the whole definition of order, everything is just about doing modular arithmetic modulo P. So we're not really talking about integers exactly. We're talking about their congruence classes modulo P. And
Right.
so in that case, there's only one element that's a multiple of P, and that's the congruence class of P. That's the congruence class of 0. So, so what we're saying is that when you're working modulo a prime, every element has an order except for 0. But last time when we were together, I started extending this to say, okay, you guys, you got the general picture in the case where the modulus was a prime, but we can discuss the case of composite moduli as well. And then you could use still the same definition. What's the smallest exponent that you can put on a number to get something that's congruent to 1? And you will never have an order for something that's not invertible. I mean, geez, now how am I going to write stuff down for you? I need my camera. Darn it. I don't know why this camera isn't working. Oh, you know what? Maybe if I plug it into this other machine, it'll work better. See if this does anything. Ooh, yeah, okay. So now hi guys, this is my office. There's a mess, and now you see that there's the computer that's supposed to be working, and I've had to plug everything into my laptop. So apparently the camera works, but it's the computer jack in the back that isn't working. I don't know what's going on. Yes, I kind of do. I think we moved the furniture yesterday because, as you can see, we were painting my office yesterday, and we messed stuff up. So let me see now. Where should I put this? Oh, hell. Take that off. Okay, so now let me try to hey, if you want to see a nice hack, what I really should do is to turn the camera around so that you could see that I've screwed it into, my camera is attached to this swing arm lamp, and that gives me multiple degrees of freedom so I can shift things around, and that's how I'm managing to make the camera point in all kinds of screwball directions. It's a theorem that in order to describe the orientation of any object in three-dimensional space, you need a total of 6 variables, 3 for the center of mass and 3 for the orientation relative to the center of mass. So in order to have something that will get the camera into every possible orientation, you need to have at least 6 axes, 6 hinges in there to give enough degrees of freedom. All right, anyway.
Can you generalize this to n dimensions? Let's say our universe is 4 dimensions with time, then is it orientable?
Yes, well, we assume the universe is orientable. You're really taking us far afield here, but yes, actually, let me just tell you, because I worked on this one summer. It turned out to be related to algebraic geometry, but you can make people understand what it is that you do. I always have a hard time making my mother understand what I do every day. So I don't know if you guys have ever been to, like in the fall, in the mall, sometimes they'll give you these little virtual reality rides, and you sit in front of it, and I don't know, I don't remember exactly how you manipulate to have a good time. But what's happening is that there's a bunch of stuff underneath that can move this little seat that you're sitting in, and it makes it feel like you're moving all the way through space. So they give you an image of riding on a roller coaster or something like that. And so the question is, well, how many different ways can you change how it feels like you're moving through space? And in 3 dimensions, that's pretty easy to calculate. You figure out where your center of mass is, and you say, I need to be able to move my center of mass to any location in 3-dimensional space. So the center of mass has got X, Y, and Z coordinates. And then the next thing to ask is, yes, well, I can tell because of the Earth's gravity, I can tell kind of how I am oriented with respect to the Earth. So we take this vector that goes through the spine, and we say, I can tell the difference between sitting up straight versus having my spine horizontal. And so you get this I'll call it the spine vector. In order to tell the direction that it points, you can imagine a sphere that goes around your body, and you need to specify the latitude and longitude of where it sticks out in this imaginary globe. So all the possible orientations for your spine are specified by 2 more coordinates. And then there's one more thing,
which is that even if I know where my center of mass is, and if I know, for example, that my spine is parallel to the floor, there's one more thing that I could tell, which is, am I lying face down or face up? Or more generally, how am I rotated around the spine? And so that's one more angle, the spine rotation, which means, I'll just call that theta, which means that specifying all the ways that my body can be thrown around in space by this machine allows me to change 6 variables separately. So if you want to be able to change 6 things independently, you have to have enough controllers on the bottom that would allow you to change 6 numbers arbitrarily. In the setting of my vector calculus class, I could say this by saying that if you want to be able to hit all the available points in a 6-dimensional space, you need to parameterize that with a 6-dimensional space and the function that goes from R6 to R6. So if you actually peer underneath the bottom of these things, what you'll see is that underneath you is a triangle, say an equilateral triangle, that's part of your seat. And down on the floor somewhere, there is another equilateral triangle, say, turned the opposite way. And then they join these, the vertices of the bottom triangle to the vertices of the top triangle. Each one of the bottoms is attached to 2 on the top, and each on the top is attached to 2 on the bottom. 1, 2, 3, 4, 5. I'm missing one right here. So that's, you need to envision something that starts off as kind of like a triangular pyramid, but it's been twisted in such a way that you have, oops, I didn't twist it. It's supposed to be twisted in such a way that you have all these possible pairings. So you end up with 6 line segments along these edges, and the way they build it is with certain pistons that can make the line segments get longer and shorter. So what the controller does is it simultaneously changes all 6 of those lengths. Those are 6 input variables, and in response, it changes the center of mass and orientation and so on of this boat. In other words, it changes the 6 output variables. And as long as you have 6 independent controllers, well, then you can change this, change it so that the person sitting in the chair feels like they're going through every possible rotation in space. It is a little tricky to see how you would get the thing to do a complete somersault, but that's not a mathematical question. That's more of a physics and engineering question. Anyway, I faced the same problem with my camera here. In order to get this thing to be able to go forward and back, left and right, up and down, that's three variables for the center of mass. And then I can change kind of where the camera is focused on by changing the latitude and longitude. And then finally, even if I'm having you focus right on one spot in the screen, I can still rotate around it, around that spot. There's your 1 more degree of rotation. So I needed 6 hinges, 6 angles that I could change at will in my swing arm lamp. And that made me happy because I could get all the orientations of the lamp. So there you go, a little lesson in differential geometry. Anyway, you're distracted.
That's really cool.
It's very fun. And specifically what we were doing was, so in algebraic geometry, we don't like to keep track of trigonometry things, but you can keep track of the locations of these points, and every one of them is x, y, and z coordinates. So you end up with like 18 coordinates, 18 individual coordinates and various relations among them, and that's the setting for differential geometry. Okay, so the reason that I wanted to finally swing this all around is so I could prove this theorem that you were asking about. And it says this: if you have a congruence class that's in Z mod n, but it's not invertible, then this congruence class little x has no order. The order is not defined. Just like a vertical line has no slope. This element has no order. And the reason why I would do the proof actually by giving the contrapositive, say it this way: if x has an order, if it has some order k, then what that means is that, well, it means that k is a positive number and x to the k power is congruent to 1 modulo n. Well, guess what? That means that x times x to the k minus 1 power is congruent to 1 as well. And that means that this quantity right here, this is equal to the inverse of x. This number right here can be used as the inverse of x modulo n. Oops, not n. So if a number has an order at all, then that number has suddenly become invertible. So it's the non-invertible elements that cannot have an order. So in the special case where the modulus n is prime, of course you know that everything is invertible mod p except for 0. So it's the numbers that are congruent to 0 mod p, the numbers that are a multiple of p. They have no order, but every non-zero element does have an order. The fact that every non-zero element does have an order is guaranteed by Euler's theorem, right? Euler's theorem says that if x is in this other half of z mod n, not only does it have an order, but we have an upper bound on what the order is. So, this is the situation that we're in, is that we're looking at these congruence classes modulo any modulus and talking about their orders. And the one most interesting case was to talk about the elements whose order is maximal. And so this was the definition that we gave. I'm not sure if I gave the definition for a composite modulus or just for a prime modulus. We say that a congruence class, and yes, it does have to be invertible, is a primitive root if the order mod n of x is the biggest number that it could possibly be. We already know that everything raised to this exponent is already congruent to 1. So the question is, can there be anything that has its order that big? And the theorem that I started to prove for you guys last time said that you will have an order as long as you will have a primitive root as long as n is prime. And in fact, it's, well, I'll show you the situation. That's almost the only case where you can find primitive roots, is if the number n is prime. There are other cases, but they're closely related to being prime. So, so here's how I was doing the proof last time, and we kind of ran out of time. Oh, sorry, so let me state the theorem. The theorem is that if n is prime, then the number of elements of order, of any order d. Now we know that the order of an element will always divide p minus 1. That was one of our results from a previous session. The number of elements whose order is actually equal to d, if d is a divisor of p minus 1, it turns out to be phi of d. And in particular, so the corollary to this is that the number of elements, well, the number of primitive roots, can I just say it? The number of primitive roots, so that would be the number of elements whose order mod p is phi of p, which is p minus 1. Oh, I'm sorry, and I wrote p when I should be saying n. So the primitive roots are exactly the elements whose order is exactly the maximal number n minus 1. And according to this theorem, the number of primitive roots is then going to be phi of n minus 1. But one thing we know about the Euler phi function is that this is always greater than 0. It's always greater than or equal to 1. And so that tells us that primitive roots will exist modulo a prime. And this hypothesis is still applying in this corollary. So if I can prove the theorem, that will tell you that primitive roots exist, okay? It actually tells you that you have kind of a lot of primitive roots, actually. All right, so let's prove this, this theorem. So here's what I know is why don't I look at the number of elements whose order divides D instead of just looking at the number whose order is D. In fact, I'll keep track of both of these. So for each divisor D of this n minus 1, I'm going to let keep track of two numbers. I guess I'll call them A of D. So this will be the number of elements whose order is equal to D, and let B of D be equal to the number of elements whose order merely divides D. So obviously B is expected to be a larger number than A. For each divisor D, you probably are talking about more elements over here. In fact, let's think about it. If you know that the order of an element divides D, well, that means that you've got an element whose kth power is congruent to 1 for some positive integer k, and the smallest such positive integer is a divisor of D. Well, if that's the case, that would mean also that x to the dth power is congruent to 1. And conversely, if you know that x to the dth power is equal to 1, and then I ask you about the order of that element, well, once you have two different exponents that you can put on the x to get 1, we've seen this actually on a couple of occasions now. If both of these statements are true, that would mean that x to the GCD of k and d, that would also be equal to 1, which would mean, so if you have these two things, that implies that x to the GCD of k and d, that's also going to be congruent to 1, but since k was supposed to be the smallest exponent, and this GCD is a divisor of k, that would be a contradiction unless this GCD is in fact k, which is to say, that would mean that k divides d. So, this little analysis in here says that B of D is also equal to, it's the number of solutions to the equation x to the d is congruent to 1 mod n, mod the prime. Right? The elements whose orders divide D are all of the solutions to this polynomial equation. And we talked about the number of solutions of a polynomial equation when you're working modulo a prime. You can't have more roots to a polynomial than the degree of the polynomial if you're working modulo a prime. So what we have right away is that B of D is less than or equal to D. So A of D is a little spooky. We don't quite know the elements whose order is exactly D. Obviously, that's smaller than B of D, but B of D, on the other hand, that we have a little more control of. We're just counting solutions to a polynomial equation. So let me summarize that much so far. You've got A of D, that's less than or equal to B of D, and B of D, on the other hand, that's less than or equal to D. And the claim that I make was that the number of elements whose order is exactly equal to, so this is the A of D. I'm going to claim that that's equal to phi of D. So I'll put a question mark over this equal sign. This is phi of D. The other piece of information we've already discovered over here is that the elements that you're talking about in this set, the elements whose orders divide D, those are all the solutions to this kind of a congruence, and those are in total going to be all of the elements A of D whose order is exactly one of the divisors of D. So the other piece of information that we've gained from this little analysis is that B of D is exactly equal to the sum of the A of E, where E ranges over all of the divisors of D. So what we have here are these two functions A and B, which are actually in that kind of a relationship that we've talked about in the previous chapter. This is the so-called summatory function of this function. If you just stay within it's a field Z mod P or Z mod N, where N is a prime, You can calculate these numbers, A of E, for different numbers, E. You can calculate this other function. These are functions defined on integers, and as it turns out, this function is the sum of the values of this function, where you range over the divisors of D. So what do we get here? What I want to do is I want to turn this one into an equal sign, and that's going to give me, let's see, how do I do this now? Shoot, I think I'm forgetting a step in here. I'm hoping that I don't need to use the Möbius inversion formula, and now I'm starting to wonder if I need that one, the one that tells me how to get A as a calculation from the B. I think I don't need that. Let's try this. So one of the stages of the proof is I'd like to show you that these are actually going to all turn into equal signs. How do I know that? Well, for starters, I do know that B of n minus 1 itself, that is equal to n minus 1. That's actually the Fermat theorem. What is this one again? This is the number of elements in Z mod n whose order divides n minus 1. Well, or no, the number of solutions to the equation x to the n minus 1 is congruent to 1. The Fermat theorem said that every invertible congruence class mod n satisfies this kind of an equation where the divisor is n minus 1. So by the time you get to the biggest exponent that you would put onto this equation, in other words, by the time you get to n minus 1, then B of n minus 1 is the entirety. It's the cardinality of the entire set of Z mod n cross, all of Z mod n except the 0 element. Shoot. Crap. Maybe you guys can help me out, actually. I'm kind of blanking here. The first claim is that B of D is equal to D for all D. Oops. For all divisors D of n minus 1. And the second one is going to be that A of D is equal to phi of D, and I can show you how that will then follow, because if you know that B of D is equal to D, then this equation would say that for all integers D, for all divisors D of n minus 1, D itself would be the left-hand side in this equation. All right? Now, by induction on E, so by induction on E then, so by induction, we will prove that A of E is equal to phi of E, which is the statement of the theorem that I had a few minutes ago. So how do you do a proof by induction? Well, the first thing is you have to start off with A of 1. How many elements are there of order exactly 1? X is of order 1 if x to the first power is congruent to 1, and the only solution there is x is equal to 1. So there's just one element of order 1, and so we know that A of 1 is equal to 1, and that's the same as phi of 1. Okay, now if you know for values of E, if for all values of E less than, let's say, some number k, we know that that A of E is equal to phi of E. Then let's see what we can say about what is A of k itself. So some of you like to call this a strong induction. I'm going to need to know that the statement that we are trying to prove has been proven for all the smaller numbers than k. I'm going to need that in order to prove that it's true for k itself. Well, look at what this equation up here would tell us. I would have a k on the left-hand side. That's going to be the sum of all of the divisors of the values of a of e, where e ranges over all of the divisors of k. But one of the divisors of k is k itself. And then there's all the other ones. There's all the divisors of k that are less than k. And for every one of those, this summand a of e has already been proved to be the same as phi of e. Well, the next thing we need to remember is that one of the results we proved about the Euler phi function is that the number k can be recovered as the sum of all of the divisors of k of the quantity phi of k. So we have exactly the same summands, the same kind of summation on both sides of this formula. They're both taking a sum over all the divisors of k. In all but one of the cases, we've already established that the summand here matches the summand over there. So what has to be true then is that the one remaining summand, it's obviously equal, a of k will now be k minus all of these things. But if you take k minus all of these quantities for the divisors that are less than k, the only thing that will be left is a phi of k itself. So by subtracting these two equations, this one minus this one, all you discover is that a of k will be equal to phi of k. So that's the inductive step. If you can prove by induction, you can prove that a of k is phi of k for all k, assuming that you can get this kind of an equation with a known d on the left-hand side. The way I had written it before, I had b of d on there, and I only knew that b of d was smaller than d, but how do I know that it's actually equal to d? So that's the only thing left. How do I know that for every d, there are exactly d solutions to, for every divisor d of n minus 1, there's exactly d solutions to this equation? And I'm drawing a blank. It has to be, I know that it's true when I get to the biggest. I apologize, guys. I can't actually remember that step of the proof. I have to laugh because I can prove it if I knew that there was such a thing as a primitive root, but I haven't proved that it's a primitive root yet. Darn it. Let me just see. Shoot. I honestly don't remember this stage of my proof. I apologize, but I remember that if the inequality fails for any value of d, then somehow what that would mean is that it would fail for these higher values of D, and that would contradict the fact that the desired equality does hold by the time you get up as high as D equals 1 less than the prime. But I don't remember how to. Okay, I could construct a proof, but it's going to be messy. Okay, I'm going to have to cheat and just say proof to follow. It's the proof of the claim, but can I prove you the claim, show you why my brain understands why that statement is true? If you go through the steps, the rest of the steps of the proof, then you finally have proved this theorem that tells you about the number of elements whose order is exactly D, and in particular, you have primitive roots. Modulo a prime, you will have primitive roots. And when you've worked with modular arithmetic, modulo a prime, a lot, you just get used to that fact. And so let me show you how you would prove to somebody a statement like this. If someone walked up to you in the street and said, hey, can you prove to me that when D is a divisor of 1 less than a prime, that you really do have D different solutions to the equation x to the D is congruent to 1? Well, here's how I would do it. So, spirit of proof. I would begin the proof by saying, let R be a primitive root. A primitive root modulo this prime. What that means is that then all of the elements of Z mod n cross can be collected together by just looking at the various powers of this one element R. You take R to the ith power, where you range over all the values of I that you could possibly need, which is all the way from 0, well, up through but not including n minus 1. So R to the 0 power is 1, that's the identity element mod n, and then you get the primitive root itself, R, and then R squared and R cubed and so on. The very fact that R is a primitive root means that no exponent on the R will ever get you back to the number 1 until you get out to the n minus first power, and I stop short of that. So all of these things are different, and there's a total of n minus 1 of them, so you've got all the n minus 1 elements of Z mod n. So when someone says something like, hey, can you please solve this equation for me? If you give me a divisor D of n minus 1, and they say, can you tell me what are the solutions to this? I would say, well, obviously 0 isn't a solution. So all the other solutions are going to have to come from Z mod n cross. Every element of Z mod n cross can be written as some power of your primitive root. So let's just write out every conceivable solution as being some power of the number R, where the exponent is in this range. And such a power of R is a solution if and only if, well, substitute it in. R to the I to the dth power is congruent to 1. And that means that, well, that's the same as saying R to the I times D is supposed to be congruent to 1. Now the fact that R is a primitive root means that the only exponents that will ever give you a 1 are exactly the ones that are multiples of n minus 1. So this happens if and only if I times D is congruent to 0 modulo n minus 1. Now, I'm doing this in the case where D is a divisor of n minus 1. Oops, that was over here. I only care about this in the case where D is a divisor of n minus 1. So I can take this congruence and divide both sides by D. So that happens if and only if I is congruent to 0 modulo n minus 1 over d. If d is a divisor of n minus 1, I need to look at the complementary divisor, and I will have to be a multiplier of that. So that means that I is of the form, well, let's say it's j times e, where e is this number, and j ranges over all the possible integer values. You can start at j equals 0 and then just keep going. Now, mind you, you don't want to go too high. If you take a value of j that's at least as big as d, then you'll have wrapped around. You will have written, I mean, already by the time you get to j equals d, you'd have d times e. D times e is exactly n minus 1. And now you've chosen an exponent, this I, which would be outside of the accepted range. So you want to keep the i's less than n minus 1, which requires j times e to be less than n minus 1. So j itself is less than n minus 1 over d. I mean, e itself is less than 1 minus 1 over e, which is d. So these are exactly the solutions to the original problem. And you can see that there are d of them. There are, in fact, exactly d solutions. And not only do I know how to count them, I know exactly what they are. They are all the powers of r to the e. There's r to the e itself. Well, there's r to the 0, which is 1. And then there's r to the e, and then there's r to the e squared, and so on. Every one of these has the feature that when you take the dth power of this, you will get something congruent to 1, because r to the e to the d is r to the, well, here's e times d will be n minus 1, and so you'll have a power of 1. By Euler's theorem, that'll be a power of 1. So I know that there are exactly d solutions because I even know how to find them. In fact, I can see that they are all powers of just a single element. So the solutions of the equation, where did it go? The solutions of this equation, the solutions of this congruence are easily identified, and then they're easily counted, which gives me the proof of this claim. So I know this isn't really valid mathematics because I just did some circular reasoning. I'm trying to prove that primitive roots exist by proving this, but I proved this by using primitive roots. And I apologize because I can't get my brain to stop thinking about this proof. So I'll have to bring that for you next time. But in the meantime, well, you've started to see a pattern here for why people care about primitive roots. We use these things to have a form of describing what all of the elements of Z mod P look like. Aside from 0, they're all going to be just powers of this one element R. And a lot of multiplicative questions are then answered by just starting by saying, well, take your element and write it as a power of the primitive root. All right, so I mangled that proof, I apologize, but when done properly, it does assure you that you have primitive roots modulo n if n is prime. And I said that that's kind of the only circumstance in which you will get primitive roots. It's not true. You can also have primitive roots modulo a power of a prime. In fact, I would like that, I'll give that as a final theorem for today. Primitive roots exist modulo p squared, if p is prime. So a primitive root in this case would mean you want to have something whose order mod p is phi of, whose order mod p squared is phi of p squared. That'll be p squared minus p. So we haven't raised things to that kind of an exponent before. But actually it's not hard, because here's what I would do. Choose a primitive root mod p. Oops, mod p. So that's something which has the power, the feature that when you raise it to the p minus 1 power, you'll get something congruent to 1, but no lower power will be congruent to 1, even modulo p, let alone p squared. That might or might not turn out to be the primitive root that I need mod p squared. So the other alternative that I'm going to use is to let S be equal to R plus P. So then you'll notice that R and S are congruent to each other modulo P, but they're not congruent to each other modulo P squared. Okay, and it's modulo P squared that I'm supposed to work, but I sort of temporarily work modulo P. Here's what I mean. Let's try to decide what are the exponents that we can put on in R to get something that's congruent to 1 modulo P squared. So take any exponent and ask yourself if whether or not R squared is congruent, R to the K is congruent to 1 modulo P squared. The answer is sometimes yes, sometimes no. It depends on what K is, first of all. We know that if this is true, if it's congruent to 1 modulo P squared, then that would mean that R to the K is congruent to 0 modulo P as well. And since R is a primitive root modulo P, well, your number K has to be pretty big. That means that K is a multiple of P minus 1. Okay, well, it might have been R to the P minus 1 power. Maybe that is already congruent to 1 modulo P squared. If that's true, you did not find the primitive root there. Okay, if R to the P minus 1 power happens to be congruent to 1 not only modulo P, but also modulo P squared, well then, sorry, that R is not a primitive root. But then in that case, if K is equal to, for example, P minus 1, then let's consider what happens to S to the K power. Now, mind you, S and K, R and S are congruent to each other modulo P, so S is also a primitive root mod P. Either one of them could work mod P because they're congruent mod P. But if R to the K power comes out to be congruent to 1 modulo P, S to the K power won't necessarily be. I mean, if you actually expand this out, this is R plus P to the K power. And, well, use the binomial theorem. Here's R to the K, plus the next term is K times P to the first power times R to the K minus 1. And then you have other terms with the binomial theorem that are all going to have P squareds in them. So S to the K, in fact, is going to be congruent not to R to the K, but rather it's congruent to R to the K plus this multiple of P times R to the K minus 1. So modulo P squared, all of that drops out. I'll keep the R to the K. And then I'll observe that I've already got a factor of a P in here. So I just need to know the value of R to the K minus 1 modulo P. I don't have to worry about what it's congruent to modulo P squared. By the Fermat theorem, this part is actually 1 more than a multiple of P. So when you multiply it by a P, now you have something that's P more than a multiple of P squared. So this part is going to be congruent to P modulo P squared. Okay? So if you happened to get a 1 when you looked modulo P squared, then R wasn't a primitive root. But S now will be, because when you start taking Ks that are multiples of P minus 1, what you're going to do here is to add in every possible multiple of P modulo P squared to the thing that you already had. And taking successive higher and higher multiples of P minus 1 is just going to run you through every possible number mod P squared that was congruent to R to the K modulo P. And you won't ever come back to just getting a 1 modulo P until K is equal to a multiple of P. So this one now, this is not congruent to 1 modulo P squared until the K is not just a multiple of P minus 1, but you have to wait through this multiple of P minus 1 until you get there. Then you'll have a multiple of P squared in this spot. And that, you notice, is equal to phi of P squared. So I have found the smallest possible exponent that I can put on S and to get something congruent to 1. And the answer is it didn't happen until until this many steps in, until phi of p squared steps. And what that says is that S is then a primitive root, modulo p squared. So I've not only proved the existence of a primitive root mod p squared, but I've even given you a recipe for how to find it. Take your primitive root mod p and just try it. And if it isn't by itself a primitive root mod p squared, then when you add p to it, then you'll have a number that will work. Okay, as usual, I went way over and I apologize for that. Listen, I owe you guys the final proof of this existence of the primitive roots modulo p. I'll have to save that for next time. Also, I'm in the middle of getting an answer key for you for the test. So I think I'll post that on the web page and on Canvas, so you can see what some solutions would be to the problems that you worked on in the exam. All right, sorry about the technical difficulties today. I still haven't figured out what happened, but I'll try to fix it before Friday.